Hello guys, welcome. Hope you all had a great day. Today let us solve some questions on number system. So without any further ado, let's get started. First question. A number 15b is divisible by 6. Which of these will be true about the positive integer b? Okay. So let's see the options. B will be even, B will be odd, B will be divisible by 6, both A and C. Okay, so what they have given? They have given 15B is divisible by 6. Okay, so for any number we already saw to be divisible by 6, we want them to be divisible by 2 and divisible by 3. You can see 15 is already divisible by 3, but 15 is not divisible by 2. So we get B must be divisible by 2. So if B is divisible by 2, what it means? It means B is an even number. So that is the first option. And automatically if B is even, it cannot be odd. So the second option is wrong. What about C? B will be divisible by 6. Is it necessary for B to be divisible by 6? No, right? We already found that B should only be divisible by 2. It is not necessary that it should be divisible by 6 because 15 already has the factor 3. Hence, 15 is divisible by 3 and B, it is just enough for it to be divisible by 2. So I'll give you an example. Take B equal to 2. So 15 into 2 will be 30. You can see clearly that B is not divisible by 6. However, 30, which is nothing but 15B, is divisible by 6. So 15B divisible by 6 does not imply B divisible by 6. So this is also not necessarily. The reverse is true. If B is divisible by 6, then 15B is also divisible by 6. But the opposite, if 15B is divisible by 6, then B need not necessarily. Necessary means always. So not necessary means not always. B divisible by 6. Okay. So D option is both A and B, A and C, which is again wrong. So the correct answer is option A. Okay, let's go to the second question. Find the units digit of the expression 55 power 725, 73 power 5810 plus 22 power 853. Wow, it looks like such a huge number, right? But we already know from reminders theorem, even this big number can be simplified and it is very fairly simple to solve this kind of questions. It only takes some math work to do. Otherwise, it is almost solvable and very easy to solve it. So they are asking us to find the units digits. So we have to remember that any number, if we divide by 10, if we divide by 10, then the remainder will give us the units digit, units place digit. So if you all agree with this, and if you don't agree, go back and see why, try to think why it is always true. So if you all agree with this, then 55 power 725 is nothing but 55 into 55 into and so on 725 times. So this remainder, using remainder theorem, if you want 10, then 55, each of this numbers remainder, it is just enough to take each of the reminders of them. So it is 5 into 5 into 5, 725 times. So what have we done? We have simplified 55 power 725 to 5 power 725, right? And now 5 power 725, any exponent of 5, any power of 5, right, will always end in 5. For example, 5 power 1 is 5, 5 square is 25, 5 cube is 125, 5 power 4 is 625. You can see any power of 5 ends with 5. So this is a rule. So if you again divide this by 10, the units place will still be 5. So we have simplified it to 5, correct? So the first term we simplified to 5. Very easy, right? So now let's go to the second term. I'll use a different color. 73 power 5810. Again, using remainder theorem, we can straightforwardly write this as 3 power 5810. Only the units digit matter. And for 3, if you see the powers, 3 power 0 is 1. So we'll start from 3 power 1. 3 power 1 is 3. 3 power 2 is 9. 3 power 3 is 27. 3 power 4 is 81. And 3 power 5 is 243, and so on. If you see the units digits, just check the units digits. It starts from 3, it goes to 9, it goes to 7, it goes to 1, and again it comes back to 3. Again, if you again keep multiplying, it will just follow this cycle. So let's check the power. So it repeats cycle of 4, right? Every 4, after every 4 numbers it again repeats. So we can conveniently write this as 4n plus 1, 4n plus 2, 4n plus 3, the powers plus 4, and assign the unit digits for each. For example, 3 power 1 is of the form 1 is of the form 4n plus 1, right? N equal to 0, we'll get 1. So for this, the number unit digit place number is 3. And for 4n plus 2 we have 9, 4n plus 3 we have 7, and 4n plus 4 is nothing but 4n itself. So for that we have 1. Okay. Now what we want to find, 5810. So 5810 we'll divide by 4 and see what remainder we get. 1 time 4, 18 is 4 times 16, 21 is 5 times 20, 10 is 2 times 8. So we get the remainder as 2. Right? So for remainder 2, what is the digit? 9. So this is nothing but 9. So the second number also we found as 9. So here we have to add, because the original thing is addition. So now let's check for 22 power 853. Okay. 22 power 853. Again using reminders theorem. This is equivalent to 2 power 853. Now we'll check the powers of 2. 2 power 1 is 2. 2 power 2 is 4. 2 power 3 is 8. 2 power 4 is 16. 2 power 5 is 32. 2 power 6 is 64, and so on. Now if you see, it goes in the cycle again. 2, 4, and then 8, and then 6, and then comes back again to 2. So this is also a cycle of 4, right? So again we'll take 4n plus 1, 4n plus 2, 4n plus 3, and 4n. So this is 2, 4, 8, and 6. And we want to find 853. 853 divided by 4. So 2 times 8, 0, 5 is 1 time 4, 1, 13 is 3 times. So 12, remainder is 1. So for 1 it is nothing but 2. So this is equivalent to 2 by reminders theorem. So this number is 2. Now we can just add this. Now it is simple, right? 5 plus 9 is 14, plus 2 is 16. So 16. What is the unit digit of it? 6. So the answer is 6. Excellent. So this is the power of reminders theorem. Maybe at first time when you see this, it might be little overwhelming for you. So I request you to go back and try it in your own time. And you can also take numerous examples, other examples, and try it out to get a good catch of this theorem. And this is also a good way to solve these questions easily instead of like using a calculator to find this expression. Maybe sometimes even the calculator may not be able to add or represent such large numbers. Calculator also has some digits of accuracy, and it cannot go beyond it, right? Okay, so now let's go to the third question. So 16 power 5 plus 2 power 15 is divisible by A 31, B 13, C 27 and D 33. Okay, let's check. Okay, how do we approach this question? First we look at the question and see if we can simplify it further. So you can see 16 and 2 power 15. Can we simplify it further? Okay, 16 is nothing but 2 power 4, right? So 16 power 5 is 2 power 4 power 5, which is nothing but 2 power 4 into 5, which is 2 power 20. So 16 power 5 plus 2 power 15 is nothing but 2 power 20 plus 2 power 15. Now we can take 2 power 15 common out, and then we are left with 2 power 5 plus 1, right? Okay. Now if you see the options, all are odd numbers, and here this one contains only 2, but for them to be divisible by any one of this option, they should at least have one odd prime factor, right? But all of this is 2, so this we can neglect. So it is only sufficient if we check for this, because this remainder is never going to be 0. So we'll just check for 2 power 5 plus 1. Again, this if you check, it is straightforward. 2 power 5 is 32 plus 1 gives 33. So it is divisible by, is it divisible by 31? No. 13 into 3 is 39. So again, this not divisible. 27, never. 33, yeah, it is divisible by 1. Factor of 1, right? 33 into 1 is 33. Straightforward. So 33 is the answer. Option D is the answer. So for this kind of question, as I already said, try to simplify the question itself as much as possible, and then try to get any kind of constraint from the options, and then you can solve it very easily. The more number of constraints and information we have regarding it, the lesser effort we need to put in to solve the question. Okay, let's quickly jump to the last question. Question number 4. So this is a standard question. So before going into the question, I need to explain what is this representation. 47 exclamatory mark. So what is this exclamatory mark? It is called as factorial. So what is a factorial? So factorial of any natural number n is given by n factorial, this is the representation, is equal to n into n minus 1 into n minus 2 into and so on up till 1. This is same way as writing 1 into 2 into 3 into and so on into n minus 2 into n minus 1 into n. For example, 6 factorial is 1 into 2 into 3 into 4 into 5 into 6. So it is just, instead of writing this big expression, it is just simpler to write it in this format, and it is called as factorial. Okay, so what, again we'll go back to the question, and they are also saying something called trailing zeros. What do we mean by trailing zeros? You take any number, 2000 and again some number. So the zeros at the last beginning from the unit digits and how much continuing it can. So the number of trailing zeros here is 3. If you take 20, the trailing zero is 1. 1020, again the trailing zero is 1. You should not count these zeros. Only the zeros at the end matters. Okay. Another example is 300. The trailing zero is 2. So this way. Again 10,000. The trailing zero is 4. So this is the concept of factorial and trailing zeros. And they're asking to find the number of trailing zeros in 47 factorial. So what is 47 factorial? 1 into 2 into 3 and so on up to 45 into 46 into 47. And there are also so many numbers in between. Now they're asking to find the number of trailing zeros. If all these numbers are multiplied, we'll get some numbers and finally we'll get some zeros. We may or may not get, we need to check it first. But if we get, they're asking what is the number of zeros that we get at the end. Okay, so how do we approach this question? So first we need to see why these trailing zeros are coming. What is that causing these trailing zeros to come? Yes, if you had guessed it right, it is nothing but the factor of 10. So 20 is nothing but 2 into 10. You can see if there is a 10 in the multiplication, then you will get one trailing zero. Right? So 10,000, it is nothing but 10 into 10 into 10 into 10. 4 tens you have in the expression. So you have 4 trailing zeros. In 300, it is 3 into 10 into 10. So you have 2 trailing zeros because of 2 10 factors. Similarly, for any number, if you take, the number of trailing zeros will be equal to the number of tens that can be present in the given number. You can say the factors. So if to get a 10, what we need? We want 1, 2 and 1, 5. Right? 1, 2 and 1, 5. If we have, let's say I'm prime factorizing any number x. And in the prime factor, I'm getting some 2 power n1 factors of 2 and 5 power n2 factors of 5. So n1 factors of 2 and n2 factors of 5. So number of tens will be minimum of n1 comma n2, right? Because whatever is, let's say 2 power 3 into 5 power 2. So 2 power 2 and 5 power 2 will join to form 10 power 2. But the other two will not have a factor of 5 to form 10. So we only get the minimum of n1 and n2. Okay. So with this much knowledge, we'll be able to solve this. So if you see 47 factorial, 1 into 2 into 3 into 4 into 5 into and so on, 45 into 46 into 47. Now we'll find number of 2's and number of 5's. That is sufficient. But can we still reduce the problem further? Yes. So if you check for number of 2's, we have 1, 2 here. So all even numbers has 1, 2. And where are the 5's occurring? 5 is occurring once in 5, then in 10, then in 15, then in 20. So 5 is occurring only in the multiples of 5 and 2 is occurring in the multiple of 2, and which is nothing but the even numbers. So if you take any consecutive natural numbers, you can see number of even numbers is greater than number of multiples of 5. Right? This is only true for the consecutive natural numbers, right? So here it is consecutive. Consecutive meaning one after the other. 1, 2, 3, 4, 5, like that way. So it is only sufficient to find the number of multiples of 5, right? So now let's check 5, 10, 15, 20, 25, 30, 35, 40, 45, right? After that 50 is not present in the 47 factorial. So number of multiples of 5 in 5 is 1. Here also it is 1. Here also it is 1. Here also 1. 25 is nothing but 5 into 5. So here it is, I'll put it as 1 plus 1. Again here it is 1, 1, 1 and 1. So how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 trailing zeros. Okay. So this number 47 was smaller. Suppose they give some large number, this factorial. How do I find it? Right? So can you think? You can take some, pause the video and take some minutes to think. Okay. Now let us continue. So you can see the multiples of 5. So 47 I have. To get the number of multiples of 5, I just need to divide this by 5. I'll get the number of multiples of 5, which is 9. Right? So all this, let's say the quota of 1 is covered. Then what I do, I take 47 itself and divide it by 5 square, which is nothing but 47 by 25. This is nothing to get these such factors of 25, because factors of 25 will have 2 5s, right? They will have 2 5s. So one of the 5 is already counted here. So to count another 5, I'm just dividing it by 25, 5 square. So 47 by 25, it will give me 1. So this I'm only taking the integer part of the division. Only the quotient is sufficient, because like it stops with 45. It doesn't take 46 or 47. Next is only 50. So it is just sufficient to take the quotient alone of the division. And to see the next thing, if you see 125 will have 3 5s, right? Because it is 5 into 5 into 5. So factors of 125 will have 3 5s. So to account for that, what I should do? The given number I should divide by 5 cube, which is nothing but 47 by 125, and take the remainder of quotient of that. So in this case, this is 0. So once we reach 0, we can stop there. So and then just add these. So 9 plus 1 will give you 10. So similarly for this number, if you want to find 10700, we first divide by 5. So what we get when we divide by 5? So this is 2, 1, 20 is 4. So 2140. Now take 10700, divide by 25. So for this you can use calculator. This gives 428. Again 10700, you divide by 125. This gives 85. 5 power 4. What is 5 power 4? 625. This gives 17. Next is 5 power 5, which is nothing but 3125. So 10700 divided by 3125. This gives 3. Again 5 power 6. 5 power 6 is, using calculator, 15625. You can see the denominator is greater. So this will give 0. Now you just need to add these. So 2140 plus 428 plus 85 plus 17 plus 3. This gives 2673. So there are 2673 trailing zeros in 10700 factorial. So if you just try to put this expression in the calculator and check, obviously it will run out of digits to display to you. So the easiest method is this way, and this is the standard method they use to solve these type of question, and it is also a very frequent questions. This you can find almost in every examination. Yeah, so I hope you learned something new today. which will be useful for you along your preparation. So go back and also try to solve these kind of similar questions so that you can also like develop what you say accuracy and speed in solving these questions. Okay, have a nice day. Thank you.